I think for me it was maybe the most difficult topic in deep learning, more difficult than attention or transformers, but that was maybe because of the order in which I learned things. So hopefully for you it will be not so complicated, and hopefully I can explain very well to you. So today we look at, let's say, refinements of the recurrent unit that we already have. Okay, so it's not really, so at the input-output behavior or input-output signature, what goes in, what could go out, it's exactly the same. It's the recurrent we saw last week. So there is no change in input-output signature. But we will see that maybe we want to do this recurrent unit a bit more in a more sophisticated way. Okay, so we will talk about gated recurrent blocks first, which are called grooves. Maybe you've heard of grooves, gated recurrent units. And then we talk about LSTMs, and finally about this topic of vanishing and exploding gradients and what this has to do with this with these two solutions. So let's first look at the grooves. So what we had last week was that we we have an internal state of some dimensionality. This dimensionality here is M, and it's the hidden layer dimensionality. And this is updated based on its own previous state and the next token that is being read from the input. Yeah, that's just the formula that we had last week. Yeah. Then we have a bias term, which is necessary because we put this into a usually nonlinear activation, like a TAN-H, or could also be a riddle. And then we want to calibrate a bit the decision threshold, and this is why we want to learn a bias term here as well. Okay, now there are two important limitations or problems with this idea. What do you think? Maybe somebody already knows this. So you haven't worked too much on the homework exercise yet, as I saw. So maybe then you would know already, or would have noticed some of the problems. So one problem here is, so last week I explained, I mean, what's the idea of this H? I explained this like the way how I see the world, right? This is how I explain this. Okay. So, but now the point is that the way how my previous state, my previous way how I see the world, this here does not depend on the input, on the current input. So the current input influences the next state, but it does not really influence how I immediately incorporate this knowledge here. Okay, so this is a bit, this is one limitation. That means like, but maybe depending on what I currently see, I should put more or less emphasis on some parts of this. And I cannot really do this effectively in this sum representation. Okay. So this is one problem, and the other is this vanishing gradient problem. Which we have down here. So the influence of the last internal state on the next internal state is really fixed and only influenced immediately by this matrix, nothing else. And the question is, we want that this state depends on xt. This is already the case. But we do not only want that the next state depends on xt, but also that the way how the previous state is being treated in this update is also somehow has something to do with x. Because if not, then we cannot decide which parts of this to keep or to forget or modify, other than a plain addition here. Okay, and this could be a bit too weak. So like considering xt in the update only in this additive way could be a bit too little. Okay, so that could be a problem. And now if the sequence is large, then we do this update formula a lot of times, and that will produce almost for sure problems in the computation of gradients. For now, let's just keep it like this because that's the third part of the course of the class today. And let's first look a bit about this contextualization of these things. So when I prepared this class, I actually remember the question by Ricardo, because he asked, okay, how do we initialize the age? 0. And I said that you typically learn it. Yeah, you can also learn this or do something random. And I said that typically you wouldn't set it to 0, but I later found out that actually having it equal to 0 is even the default configuration in PyTorch. And it's not, I first thought during the class, I thought it would be a problem because then I multiply things with zeros and I don't learn anything, but actually it's not the case. It's just like, because the hidden, it's not the weights that is 0, but it's just the state. So if the weights are 0, then you have a problem. But if the state is 0, you still have the bias term and so on. So then you can actually learn something. So it's a possible choice. Maybe it's a good choice, maybe not. It's the default choice in PyTorch, but also only because it's not clear what else we would do, except something random maybe. But there is actually an advantage in, like, let's say a deductive advantage in assuming that the initial state is 0 in all dimensions. So for now, suppose that, let's assume for this class that H0 is a 0 vector, okay, of size m. Okay. Now, why is this? That clear what I'm saying? Yeah. So in the last slide, so we would say that here this value for H0 is 0. So we have nothing to start from, so to say. But that only means that this part here is 0 in the first iteration. But still, we will then bootstrap from here on. Okay. So if this is so, then we could have an interesting interpretation. And we could say that if we go back to the formula for a second. So let's take this product here, or even the whole this whole part here. So that would be somehow the influence of the previous hidden state onto the current hidden state. Now, what would happen if we would now allow to set this here is a vector, okay? Because here we have a matrix multiplied with a vector plus a vector. So this is a vector, right? Now, what would happen if we would allow some of these entries of this vector here to be set to 0? That would be basically meaning that we would ignore this part of h t minus 1, right? If we set it to 0, we would basically ignore it, and it would be somehow be the same as we would pretend that for at least these dimensions, not for all of them, but for some, we are again in the initial situation. It's a kind of reset. Yeah? But it's only a reset if we say that initially everything was 0. Otherwise, we don't have this interpretation, but this is why this is handy. Okay, so if we would say, okay, yeah, we keep all of these, but for some of these entries, we set the value to 0 instead of this value, then it would be like, either you take what you have here or you reset to the initial part, but not for all of the entries, but only for some there. Yeah. Okay, this is what a gate does. So a gate is a vector of zeros and ones, okay, with m entries. So G is a 0, 1 vector, binary vector. Now, if we now would multiply the hidden state with such a gate, then we would keep some of the hidden information the hidden state. This is where we have the ones, and where we have the zeros, we would erase this information and go back to the start. What's this funny symbol? I think everybody should have seen it in my class at least. This is the Hadamard product, which is simply I take the two vectors and I do a multiplication position-wise. So this is the first position with the first multiplied with the first position here. Next entry, second position of this times the second position of this. Okay, so this is a very simple. It's like a point-wise vector multiplication. Okay, so and the interpretation can be a bit. One is I preserve the information, I remember the information in age, and zero is I forget the information and reset. Okay, so the problem is that, I mean, this looks a bit harsh, 0 or 1, because in the end, okay, it is already clear that we want to somehow compute this G. So, I mean, because where does this G come from? We will not set some random set up some random vector, but this should be something that should be learned. So he should somehow later learn which part of the hidden state should I remember, which should I forget? Yeah. But if you should learn something, we need something differentiable, because otherwise we don't have backpropagation. Now, if we have 0, 1 values, this doesn't look very differentiable. I mean, how do we get value 0, 1? It's like a step function, a switch. Either it's 0 or it's 1, but it cannot be anything in between. So it cannot be, so the activation we have here cannot be anything differentiable. Or maybe it's differentiable, but the gradient is 0 everywhere. So it's not very useful. What we need is a kind of continuous gate where the values are not 0 or 1, but between 0 and 1. So that would be a kind of partial remembering. Values close to 0 mean that I'm strongly forgetting. Not everything, but I'm getting pretty close again to my initial state. And values close to 1 means I remember most of the stuff I have in the hidden state. Is this clear, or?
I kind of drop out on the fly, but it's not directly.
Okay, this is a very good comment. So this here, if you have the binary version, this would be a dropout.
Yeah.
But a dropout is a random condition, and it's not something that you learn. So it's just, so dropout is kind of gate that you apply randomly, but only during training. And this here is something that we want to learn systematically, and we want to use it also in the prediction. But yeah, the effects are a bit similar. Okay, so let's have an example. So this is now the first time in the course that you can do something with pen and paper. So let's say that the previous hidden state is this one, and we have this gate here. Okay, so what would be the updated state if we just multiply it like this?
0, 1, 1, 0, 5.
The rest of the form elements are 0. And the rest is retained. Yeah, exactly. So here, the first and the fourth element is forgotten. So it was a bit too easy, but don't worry. So we're getting there. So
it can complicate it.
Yeah. No problem. Actually, it's going to happen faster than this. Oh, okay. So now let's consider some continuous gate that does not have values just 1 or 0, but like this. So then we can do the same operation, but we will not completely. Well, okay. Here in this case also we completely forget the second field, but and we perfectly remember the third field, but the first one is mostly forgotten and the fourth one is mostly retained. So how would this be reflected in the first value? Actually, that's a very nice example. It's from the book, but I only recognize right now why it is nice. So
We have 0.09.
So in the first entry, we would have minus 0.094. Yeah. In the second entry, we would have. In the third entry, we would have 0.39. And in the last one, 0.45, right? So this here is, I think it's nice because you have completely forget, mostly forget, completely remember, mostly remember, and something in the middle. Yeah.
What is the criteria for the G vector? How I define this?
You don't define it. That's my whole point. You don't define this.
Random?
No.
No.
This will be learned. So currently, you have no idea where this comes from, but I explain it to you in a second where it comes from. Then it will be learned. Okay. But you can tell me. I mean, I need values for G between 0 and 1. How would I get that?
Here's
From the previous.
how to compose the third.
I need a vector that has only values between 0 and 1. How can I make sure that I only have values between 0 and 1?
You ask my.
Yeah, now who of the two is right? Because both are right, but one is more righter than the other. So the softmax gives me values between 0 and 1. And
all of them sum
yeah,
one, and that's not a one in this case.
so we do not want a probability distribution. We only want like activations between 0 and 1. So the logistic function would be pointwise application of the logistic function would be more appropriate here. Okay, so now what does a gated recurrent unit do? So we take what we did before, only that, so this is exactly the same formula as before, only that we do not say that this is now my new state, but let's say we introduce an auxiliary variable, temporary variable. So this is kind of update candidate. And in the standard recurrent unit, then we say, yeah, this is also the new HT. But now we want to say, yeah, okay, I want that this influences the new HT, but maybe not completely. I also want to retain some information from before, okay? So the way to combine this is then through a convex combination. So you say the new state is the old state multiplied with some forget gate. This would be our G now, okay? This would be our G. And we say, but to another portion, it will be the what we want to update according to this rule here. So phi, this is the G, okay? So here we only have values between 0 and 1. And why? Because we apply a logistic function to something. Let's discuss this in a bit. But so here we have a vector only with values between 0 and 1. And here we have the counter values, so to say. Okay. So you say that my new value is the old value multiplied with phi plus the like processed new values according to the standard regression recurrent formula multiplied with the counterweights. Now, what would happen if we would forget everything? If we would forget everything, then all of these entries here would be 0. So we would have a 0 vector here. Yeah. But then 1 minus the 0 vector would be the 1 vector, and then we would just have this update. So in other words, the standard recurrent block is a special case of this, where we forget everything we had before. And then I have exactly the same behavior. Now, what's the other case? The other case is that I remember everything and I do not incorporate my new knowledge. Then this would be the 1 vector But if this is the 1 vector, then this is 1 minus 1 is the 0 vector. So I would basically not update at all. So then if I remember everything, then my new state would be exactly the same as the old state. And in this case, I would basically also ignore the new input token, because the new input token is then, it's not contained here. So, okay. But I can have things in between. I can have then partially forgetting, partially remembering. Okay. Now, what's the gag here? And why is this something cool? Because now I can control in this phi, which is the G, and we ask where does this G come from? So this gate here is, okay, a logistic function to have values between 0 and 1, but what does it depend on? What does so these gated values here, where do they come from? What do they depend on? And they depend also on the current input token here and the last input state. And then I basically use the same type of formula, only that this matrix here is a different one. Okay, so here I have a matrix that tells me how should I consider the current token for my forget behavior. And how should I consider my current internal state for my forget behavior? And I have some bias term for this too. Okay, so that means that now I can, before I just had a fixed way of considering my my previous state was just multiplied with some constant weights, and that was the way how it influenced the current state. Nothing else. But now I have much more flexibility, because I can say, okay, based on my current state, I can control how much I want to forget or how much I want to remember. Okay, I could do this before. And also I can use the current token to decide how much I want to forget or where I want to forget something, and where I want to retain something. So, for example, and it should be immediately clear that this is somehow very useful, because you could say, okay, if my next token is a certain word, then I know that I can close a particular context. That is now also. So you read the word river, and before you remember it, before you saw, for example, the bank token, but you were not sure yet about the context of that. But then you see the river, and then you can close basically everything in the context that was like still having doubts about the concrete meaning of bank. Okay, so it somehow means I can. I can now control not only in a superlinear way how my previous state knowledge is incorporated, but I have 3 more screws. This one, and this one that controls how the previous knowledge should be incorporated into the new state. So this is an enormous increase in flexibility. So this increase in flexibility also comes with an increase in the complexity if we want to draw the graph, okay? So before, what we had before was this, and this, right? So, and we had a loop here. So before we had, if xt goes into ht, and ht goes also into itself. That was the loop before. Now things already become much more complicated, but believe me, it's still simple. Okay, so so we say ht is now updated based on what? On ut and on the forget gate. Okay, so here we decide we want to have so we want to have this value. This is the weight. This is like the gate between 0 and 1. This portion we want to keep of the current one. So this is why these two go together. into this Hadamard multiplication, okay? And we have something new that we might want to consider. The new thing is the update. And the update depends on our current internal state and the new token, okay? I mean, this is just the formula we saw on the last slide, but now in a figure, yeah? And now we have the two pieces of information. This guy here, they go into a Hadamard product and are multiplied with a weight matrix. So these two here come together and then define together in this multiplication here the new state for HT. Yeah. So why is now what is a bit confusing here, and I mean, why is this here in a double framed box? This guy, I mean, this is just our notation for a gate. Okay. Now, what is a bit strange is that the gate in itself really is there is nothing learnable right here. This is just a function that tells you how you have to multiply some things. Okay, but this is sometimes the confusing part. So in the first slide on the grooves, when I didn't have the phi yet, that was still the G. Okay, and here we just say how is the G being computed. This here is the sigmoid. Basically, what is inside of this, what we don't see on in the figure, is here we have the sigma. This is the logistic function applied to this weight matrix multiplied with the current state information. This is why this is being written here. Yeah, plus the current input token multiplied with this matrix plus a bias term. So we have this times this plus this times this plus the bias term, and this together goes into a logistic function, a sigmoid, that will activate or not activate. So activate means remember. This deactivate means forget. Yeah? And this comes then out here. And what we want to remember, what we want to remember, that's multiplied here at this point. So here is the remember part. Here is the forget part, because forget means update or incorporate the update. The more you forget, the more you update. The more you incorporate the new knowledge, and then they come together into this new state. Already a bit involved. Yeah. But I hope that it becomes clear why this is advantageous. Why this is advantageous? Because now, before, this guy had to play too many roles, and actually it was like only living we were only living in the present. But now we can also live a bit more in the past, because we now have a way to return a bit to this initial state, and at least in some parts of the hidden dimensionality, in some parts we can again start from scratch. So this, if I should describe this. Or the key innovation or the key contribution of this construction, it would be the ability to reset. The ability to reset. Okay, good. Because before we didn't have that. Yeah? Before we only updated all the time. Update all the time, and we couldn't go back to the start. Okay, so these units introduce quite some new notation. So we had 3 new parameter structures that need to be learned. Yeah? So we need to learn more. Why? Because we need to learn these weight matrices that control how the input and how the previous hidden state control the forget gate. So this needs to be learned, and also a new bias term. So we basically multiply the number of parameters we have to learn by 2. Because before we had a matrix W for the inputs, WI, and we had WH, and we had B. Okay, so that we before, and now we have twice the number of parameters, but not exactly because we can choose the dimensions here a bit. No, actually not. Actually not. We cannot choose them because they also depend on the hidden dimensionality. So actually, we are doubling the number of parameters we have to learn by doing this. And in terms of computations, it's even much more because I mean, if we look at the graph, obviously, a whole lot more stuff is going on here than simply take this and put it into this. So we have many more computations we have to do. So in total, it's 8 new computations. We have 2 new matrix multiplications, this with this and this with the hidden state. There's 2 multiplications. Then we have to do 2 summations, the result of this plus the result of this plus the result of this. So 2 multiplications and 2 sums. This is for incorporating this. Then we have to apply the logistic function to each of these entries. So we have to do this multiplication, then we have to do this summation, and then we have to apply the sigmoid function. And after we did this, we have to do this Hadamard product and this Hadamard product. Actually, I even forgot to count this here. And after we did these 2, we have to do the sum, and only then we have the new H. So it's 8 new operations, so much more costly than a standard recurrent cell. More than twice as costly to compute than a standard recurrent cell. So now let's see what happens if we apply this. So let's say our last hidden state was this one, the same as before, I think. And then we say, according to the standard recurrent update rule, we would now update the state to this here. But in our case, now it's not the new value, but it's only the update candidate. Okay, so that would be in a recurrent network, that would be my HT, but for us, it's now only the UT. And now we see that, okay, we have somehow, we come through the weight matrices that we have, we come to the phi t, which we had here in the previous example, and then we also have the counter phi. So question is, what's my new HT? It's something that you need pen and paper probably to compute this. So maybe to really understand what's going on, let's really do the exercise. Everybody can do the exercise. Concrete question is, what's the first entry of HT? Let's remember that a value of 1 here means, so high values here, this is the part I want to remember. High values here means I remember the previous state, and low values here mean I forget them and I incorporate this one. But low values here mean high values here. Okay. Zero point zero. Okay, first suggestion. Minus 0.02434.
No. Minus 0.396.
Minus
396.
0.396. Other suggestions? So we already see it's not 2. We have already two different opinions. Okay, so how would the computation be? So what we need is to apply the forget gate. So we need this and the Hadamard product with the previous value, and we have to add then one minus the forget gate and the Hadamard product with the update. Okay, now. So what are these vectors here? So here we have 0.9 times minus 0.94. Okay, and then we have 1 times the first integer. So here we have 1 times 1.05, right? And so on. So, okay. So, and then this needs to be added with here, this other vector. So here we have 0.1 times 0.5. Times 0.5. Yeah. And the second entry is 0. 0 times 2.5. And so on. And I have 3 entries more. Okay, and then I see, okay, this here is roughly minus 0.81. So I forget that this here, so it's more or less this. Let's say it's approximately this plus, and here I have 0.05, and here I have a 0. So I would have a minus 0.76. And here I have no change here because I remember everything. Yeah. So that would be the idea. Okay, maybe I had. Okay, I mean, I have a rounding error there somehow, but yeah, roughly we get the idea, right? 8.5. Yeah, so the exact value is this here. Okay, so that would be then the intuition for gated recurrent unit. And if we now unfold this, so that all of this happens in time, right? So we did it now once, but this happens now for every input token. So we start with the initial state, which could be 0, all zeros, and then we apply this whole logic. Like the figure is now a bit rotated because the hidden state. So before we had that h was above the x, so it's a bit. This part here is a bit shifted for readability, but in general, it's like, okay, so I start with a hidden state, I want a new hidden state, and the new hidden state is now also dependent on x, but I have instead of putting this and this directly into H1, I put this and this into the update, okay? And based in my update candidate, that would be the standard recurrent part, so to say, this here. But then I control, okay, how much of this goes here? This is 1 minus phi, and phi of this goes into H1. So we have here the remember part, and then the remember part goes into H1. And here we have the, and here we have the update part, like the forget part, so to say. And this goes in here, and then we have an H1. And then we can do the same stuff again, but based on H1. The only difference here is that we have a new input token. And since we have a new input token, we update the forget gate. And this, for me, is the most important part here, okay? Because this part here is exactly the same as before. So here, this logic for U2 is exactly the same as before. Yeah. But what is new is that we now also use this. So this edge here, this is the crucial part, that we have an edge that, well, actually these two edges, so that we use the input token now not only to determine the candidate, but also to configure our forget behavior. And this can now go on for tau steps.
It's just a modification in the slides, the previous slide when you showed this picture. Previous one, just naming the output arrow that has the -1. It refers to the index of the H, right? So that means HT -1. That's correct.
Yeah, exactly. Yeah. So you mean these minus ones? Yeah. So all the gray edges are the recurrent edges. So here it's saying, okay, this T. So when you do this multiplication, then this T is not the same as this T.
Yeah, exactly. It's the last one.
Yeah. So if you want to compute the T, the value of this for T, then you need to multiply with the version H T -1 here.
Okay.
And the same also for, for this here, it's only this one. But in the output, it's the same. And here for the update part, you also use the previous step. So the -1 doesn't say that you multiply with -1 or so.
The index that you need to.
Yeah, the index where you have the subtraction with one. Exactly. Okay. Good. Now, all of this is basically some hidden. It would be nice. So this figure is exactly copied from the book. I am already writing the LaTeX code to change this a bit, because it would be nice to show here which part is like the internal part and which part is like more the interface part. So what did not change is that at the interface part, you have some that you have the inputs xi at every step, and that you have a hidden state at every step. So input and output, I mean, okay, here you have an explicit additional output, but the hidden state in itself can be seen as an output already, okay? So you have this input and this output at every step. This is the same as in the recurrent case. So the only thing that changed is the inner part of our function that computes this. How do we compute this? And now we do not only use the same value from the hidden state from before and the input token, but we do more sophisticated logic here to better control how much of this we want to carry over and how much we want to update. Not only to compute this update. Okay, so it's already quite tricky, but it gets better. Questions? Okay, so in some sense, it's not.
I have a problem with some words that in this case not forgetting is more like a noun. That's the reason of gate. You gate something, you pass through.
Yeah, I had the same problem when I first encountered this. But if you think of the gate as something really binary, 0 or 1, yeah. If it's 0 or 1, and if you say that initially you started only with zeros, then this makes sense. Because in this situation, you say, okay, setting everything to 0 is basically starting again from new. And that means that you forget everything that happened in between. So then the analogy works a bit. And otherwise, I mean, actually forgetting is kind of binary. So how can you forget only a portion? Why would that mean that you multiply with a value? So I understand why one would struggle a bit with the terminology, but at least in the binary case, it makes somehow sense. So it's kind of partial remembering and partial forgetting, where you say what does that mean? Partial forgetting and partial remembering, where you operationalize this with multiplication. But in a sense, I mean, I think one can, it makes sense in a way, because one can say, okay, if this output here is very, I mean, here it's clear. If I have a 0, I remember everything. This is clear, I would say. This is so as long as the values are 0 or 1, I think we are good. If the values are in between, one can say, okay, but now the closer I get to 0, the more I am again in my initial state, the more I have forgotten. So I think it makes somehow sense to think in these terms. But still, the term can be a bit confusing because it's not really that I forget something, it's I throw it away actively. It's a bit different. So it's, I mean, how can you actively forget something? It's like you cannot actually. So it's more something that happens, and here we're doing it actively, we're throwing away. Yeah. Okay, good. So then let's talk about LSTMs. So the gated to recurrent units already improved the contextualization, because we now say that the way how we can actually control a bit better what we want to memorize. In the standard recurrent network, we cannot memorize anything explicitly, but like this behavior is, or at least this behavior is not context dependent, because we always multiply ht -1 only with the linear matrix, and there is, so the recurrent unit already helped us to contextualize this forget decision. And here it's a forget decision. I decide to forget. Yeah, but this internal state has still kind of two tasks, okay, that it plays at the same time. So one important task is, I mean, let's look at the at this figure again. I mean, look for how many things this guy is being used. So it's used to configure how do we want to, how would the update look like if we only incorporate everything? If we forget everything, how would the update look like? Okay, so this is one thing. We also use it to configure how much we want to remember, and also for this multiplication itself. So this is used for 3 parts here. So this is like this auto update, right? So this edge here is for the this is the remember border, and here is the configuration of how much I remember. So here it's already 3 things, and also we use it to determine the outputs later. So this border here is what I refer to as the input interpretation. So this border here, on this border, we use the internal state to interpret the new token, because these 2 guys together give us the UT. Okay, so here we use HT to interpret the new token. Okay, but here we want to do other things, and here we also want to do other things. So maybe it would be good to disentangle this a bit. Okay, so that's the first one I was talking about, and then it also must somehow represent a general idea of the sequence. This is necessary to decide what to remember and also what to output. So maybe it's even 3 rows. We could say we have 3 or 4 rows here. One is to interpret the inputs. One is just to be a memory, something I want to remember, which I can then update. The third thing is I want to control it. I want to use it for the control of how much I want to remember and whatnot. And the fourth thing would be I use it to produce my outputs. So this seems to be a bit overloaded. And if we only think about now in these 2 things, like this input interpretation and like this general concept, maybe we should separate the issues and not have only one hidden state. So the idea of LSTM is to have two hidden states. Let's focus only on this column here for the time being. Let's forget forget all the arcs. Okay, forget all the borders for now. Let's only look at the boxes and only the boxes here in this column. So what is the same as before? We still have the input token, we have the update candidate, we have the hidden state and the output. So this is all of this is before, only we have one new thing here. This is because I said, let's separate this hidden thing into two things. Okay, so we split up H2 into HT into HT and CT. Okay. Okay, so this is the, is this me or what? Yes. Sort of. Okay, so the new thing is here in this block. Okay, and the idea is a bit to say, I want now HT to be only responsible for this first part, for this input interpretation part, but not for having a general idea of the sequence. And for this, I just want another state. Yeah, another. It's kind of a second recurrent cell. This is the CT. Okay. So, and let's now understand this step by step. So, okay, so HT is controlled to interpret the input. That means that this goes together with the XT into something. Okay. So that should be, sorry, here. So here we have this edge and this edge. So they go together into the UT. That was like this before. Okay. So this part is identical to before. UT still depends on HT, HT minus 1, actually, and XT. Okay, so this part is as before. But now we do not directly update the HT based on this UT, but we put something in between. And what we put in between is, let's call it the brain cell. So this is now, so HT is responsible a bit for the communication part, how to interpret a new message that arrives. And we want this cell to be more like a brain that is a bit decoupled from this communication that comes in and goes out. Okay. So we say this what would be the update in the other networks, that for us should be only a kind of now internally interpreted signal that goes into our brain, like the brain internal state. Okay, and now based on this internal state and the input again, like these two together, now go into my update on how should I now perceive the world. Okay. So yes, so I have two states. One is like for the communication with the with the world outside. Yeah, on the input side, and on the output side as well. So HT is like a bit like the interface, the state that controls the interface, and CT is the state that controls the brain cell. So the responsibilities would be a bit, and I'm not saying that we tell them, hey, this is your responsibility. This responsibility must somehow be implicitly clear from the architecture. But you see here that this guy goes to the output and does not really have direct influence or direct, it does not have a direct influence here on my brain cell. Yeah. So there's no edge that connects this here directly to this down here. It doesn't exist. Okay. But what exists is, so this controls my output behavior and also how I interpret new inputs. So this goes here. Okay. Well, so this is the general idea. Now, why do I need all these other connections? Basically, these are to say, but I now want to use this gated idea of to control how much to control the influence of different aspects, not only for the hidden cell. So we still have the So we still have a cell that controls how much we want to memorize of this here. That would be a bit this part here, the omega. How much do we memorize of this? So how much do we memorize and how much goes to the, it comes from the new signal? That would be a bit this here. But we also want this idea of these gates for the brain cell. Yeah. So for the brain cell, we would have it here in the phi and also in the kappa. So let's see step by step why we need now 2 additional of these. Because there are different forget and control behaviors we want to have. So let me. So when we look at each of these gates here, what do they actually control? So this guy here controls in my update of my internal state, how much do I want to incorporate new information? Just a second, let's see. Okay, so it would be around this here. So in my update of the brain cell, this guy here controls how much of my previous state of the brain cell do I want to keep, and how much I want the new representation to influence it. Okay, so this is really involved. Okay, so from here I get an update candidate, but this update candidate is not for age anymore, but for my brain cell. So UT is the brain cell update candidate, so to say. Okay. And the brain cell update candidate comes from my internal state H and the X. Okay, so this is as before, but I would use it not to update H, but to update my brains. Okay, but to control how much I should use this, how much should I update my brain based on this, and how much I should keep my current state. So for this, I use the kappa. Kappa then is a bit what the phi was before. So here I say I consider this brain update state to a degree of kappa. So this is my gate for the brain update. Okay. Yeah. So this is then the first one. Okay, so this allows me to control how much do I want the brain update vector to influence my new brain state. Okay. Yeah. And this also, how much should this new brain update vector influence my, how strongly should the brain update vector influence the update of the brain? And this also depends on my current token. Yeah? So this kappa, which controls this depends on my current internal state, but not the brain state, but the let's say interface state and the current token. Okay, so together, these define how strong the brain update vector will influence the brain update. But the brain has a previous state that will also influence, and this is this cycle here, and this will be controlled through a separate gate. So then my phi controls, and how strongly should my current brain state be preserved. Now, before we just have this formula here, we say the previous state goes with phi and the rest goes with 1 minus phi. So the change here that makes it a bit more difficult for me is that we do not create a dependency on this anymore. But we say in the LSTM, you just have a different vector for this. So here we say this is the kappa. And these do not have to sum 1 anymore. Yeah. And this makes that we have a mu symbol. This is why we have these 2 boxes. Because before you would just have said, okay, yeah, so you have the phi t and you have the 1 minus phi t. But now this is something separate, okay? And they don't need to sum up 1. And actually that's very important, that they do not have to sum up 1. And together, then they form the new state. But independently of this, then it's the same idea, okay? But both of these control the state update for the brain, not for the age. But I still want something to control the update of the age, and this is why I need omega here, okay? So these two gates here are basically what we had before for the hidden unit, but now we apply this idea for the brain unit here, and we say that they don't have to sum up 1 anymore. Yeah? So before, this is the same idea as before with phi and 1 minus phi, only that here we replace the 1 minus phi with something arbitrary, okay? So this is just the idea from before, and now we say, yeah, okay, but we want also to have a gate for the update of the interface state, not only of the brain state, also of the interface state. So we create here another connection, another gate, and this is called omega. Okay. So it looks much more difficult, and as you notice, it's also more difficult to explain it, but the essential idea is not so much more complicated. It's basically just saying, I just want to have 2 of these states, of these hidden states, and that means that I also need 1 more gate to control this behavior. But why do I have 2 gates more? Because I relax the assumption that this and this must sum up 1. And if I don't have this restriction anymore, then I have to specify this apart. Otherwise, it's implicitly clear. Yeah. Because if I need them to sum up 1, I only need this one, and this is implicitly clear from the other. But since I take out this restriction, I need to learn this gate explicitly. Okay.
I see like a layered architecture, which each function gives me how much I want to forget for the next layer. That's the way I think about it.
For the next time step.
Yeah, for the next time step.
Yeah.
And I don't give me a question.
Maybe it's better to not say to forget, but let's say how much do you want to incorporate?
Okay.
How much do you want to incorporate? So this tells the kappa controls how much of the the kappa controls how much of this update vector UT you want to incorporate into your new brain state. Yeah. And the phi controls how much of the previous brain state you want to incorporate into your brain state. Yeah, because here, and the omega controls how much of the brain state you want to consider in the update for the interface state. Now, the point is that all of this, like forget, brain state, all of this is just, I put the semantics. Here, I mean, it's just a network of functions. And there is no notion of like, forgetting or gating or, so I mean, we just do computations. But it's more like we have this idea in mind and we construct a circuit that will somehow do what we want if we manage to learn nice weights. It's like with the attention mechanism. I mean, the attention mechanism just computes something. It's completely meaningless if you don't learn good weights. But these architectures somehow create the structure, precondition that you can do something reasonable in theory. It's like with the autoencoder, yeah? And the autoencoder, this is just crap. If you do not have a meaningful loss function that will utilize this, then there will be no notion of compression. Just like you do some projections that can be completely meaningless. And here it's somehow the same, okay? So it's kind of creating a structure that can potentially help the network to implicitly do something like forgetting, memorizing, or deciding how much to incorporate, okay? But it's not like we would explicitly design the components to do that. So before we had only the phi, now we have kappa, phi, and omega. But for all of them, it's the same thing. We always say that we want to use the input tokens for these gates. We want to use the current hidden state, like the interface state. We have some, and that's it basically. And then we have some bias to control the decision threshold on the signal. So all of these three gates are basically logistic function controlled. And now instead of having, before we doubled the number of parameters, now we double again after having doubled. Because before we had, so in the beginning, in the recurrent case, we have only two matrices and one bias term. Then we had two additional matrices and an additional bias vector. So it was, or in 2 times as much. And now we have, again, we have 4 new matrices and 2 new bias vectors. So it's 4 times as much parameters as we had in the standard recurrent case. Okay, that's fine. Now, let's see a bit about the computations, because it also helps. I mean, the figure kind of helps, but also is quite complicated. So let's see, maybe at a formula level, it can be even here, in this case, easier to understand what's happening. So, or the intuition. So this is the standard update candidate as we had it before. Yeah. And then we say, and here we have the 2 update rules for the brain cell and for the interface cell. So the brain cell says, I want to incorporate the new knowledge, so to say, so the new representation of the inputs in the light of the current interface state. Yeah, so this is UT is kind of the interpreted new input token. So I have a new input token, and I want to have this input token being interpreted in the light of the current input state, a hidden state. And this is UT. So let's say UT is the interpreted input token at time t. Then the brain cell says, I want to incorporate this to a certain degree, controlled by kappa, but to a certain degree, I also want to just keep my current brain state, and that is phi. And here you see that now the difference, because before this was just 1 minus phi. Yeah, and now it's different, and they don't have to sum up 1 anymore. And this is for the learning stability, this is the important part, that these 2 guys don't have to sum up 1 anymore. Okay. And the hidden state is now like the interface hidden state is now saying, okay, that actually I should replace this by some arbitrary activation function. Doesn't need to be a ton h. But here we take the brain state and choose, okay, how much of the brain state we want to preserve. Okay. But interestingly, this doesn't have any additional input anymore. Okay, so this doesn't depend explicitly on X anymore, like we had it for the brain side. Yeah. Why does the ton H make sense? Because it creates values between -1 and 1. Then you can somehow configure this together with the gate here to steer the behavior. But I believe, I'm not completely sure by now whether this is configurable, but I think it should be configurable in PyTorch. It doesn't have to be the H function. Okay. So the main contribution of the LSTM cell is that it separates responsibilities of having a kind of brain unit that is a bit more like has a long-term vision of the whole sequence X, and this state HT, which is more responsible, like which is like this guy who is like responsible for interpreting the next tokens directly, and also preparing the outputs. And this long-term property, this is really like here in this summation. Okay, so here we have the long-term behavior. So the bigger this is, the stronger we memorize, but not we memorize our internal state of interpreting the world, but our internal state of what we understand. And here we can configure how we want to change our interpretation of the of the next input tokens. Okay, so I understand that this is not so super easy to grasp at first, but yeah, I hope that together with figures in this line of reasoning, we understand why this makes sense. And this can then also be unfolded. So of course, we have this now in every time step. So in the first time step, okay, but now we have two hidden states, H and C, and both can be initialized with zeros. And then we start going, okay? And then we do this whole process and get to H1 and C1, and then H2 and C2, okay? So we get, for the LSTM, we get twice the number of hidden outputs as we have in the recurrent or the group view. So here the input-output signature changes a bit because we have because we have this here in addition. Right now, I would have to, honestly, I would have to check. I'm not sure about this. So let's look at the documentation of PyTorch. So here we have recurrent layers. Then we have an LSTM cell. At the shapes. What?
But it's not funny to do it from scratch.
I have to do it from scratch.
Yeah. Okay. Okay, it seems that they don't give you the brain cell information, just the interface. Yeah. So in principle, if you want to have the brain cell, you can also have it. Okay. So they give it to you in the C. But they give it only, okay, they give to you the state of the CN, but only for the last iteration, not all of them. Okay, so it's a bit limited, but I mean, you can implement your own LSTM, so no problem. Okay, so it turns out that this then solves a lot of problems. Yeah, because you have just a network that it's a bit more capable because you have units with different responsibilities. He's responsible for parsing the new inputs and also, with all this communication, input and output with the rest of the world. This is what H must do. But what C must do is to have a good general idea. So he has the big picture and he has the local communication picture. This is the best way to think about it. And before we didn't have this separation, and it's somehow clear. I mean, if we think into it, it's somehow clear if you have like just one person and he must at the same time be strategic, long-term view, and also do the communication, and you only represent all of that in a single vector. It seems like it's a bit too little to manage these different roles. So this decoupling of big picture and communication, this was really crucial this is really crucial for better performance in networks. And then there is this important side effect of this vanishing gradients that improve here in these structures, which I explain in a bit, but typically, they use this vanishing gradient and exploding gradient to motivate this kind of networks. And also in the book, they do it like this. But I changed the order because I think it's more important to understand this idea of the rows of the hidden cell and the gates. Because this is really big, because there are two advantages. We have like a higher capacity a better capacity to process sequences because we have these different roles. And the other thing with the vanishing gradients, which I discuss now, is more something like on top. Okay, for me, it's not even the most important part. but together they form a really strong innovation. Okay, so let's talk about this phenomenon of vanishing and exploding gradients. So let's get back to the standard recurrent layer. Okay, so in the standard recurrent layer, I have my new value for h is what? Is some activation function applied to a linear projection of the previous value plus a linear projection of the new token. That was the situation. And now, if you remember the ML2 course, we talked about net gradients. Yeah, so net gradients are is the derivative of the error given the input of a layer. Okay, so and we denoted this always as delta. So this here basically tells me what is the influence that the inputs of this recurrent unit have on the final error. Yeah? Not so important that you understand exactly what this means, because I know not everybody has been in my course, and those that have been maybe don't remember exactly. But the point is, this here is something that I will compute during my backpropagation step. And I will multiply with this at several parts. So somehow this vector here will be important. And it turns out that for the recurrent unit, I can write this delta, which is important for the backpropagation step. I can write it like this. So it's like the derivative of the activation function. Okay. And here I have then a multiplication of the weight matrix for the outputs. And the delta that comes from the outputs, and here I have my weight matrix for the hidden units times this. And I see, oh, okay, that's the same. So I have these deltas for my hidden layer, but at different time steps. So I have a recursive connection. And now let's see why this is important. So let's suppose that we have the linear activation function. F of x is x. What's the derivative of that? 1. So if my derivative is 1, then I can ignore this part because I will only multiply with 1s. Okay? And let's also ignore for a moment the output. Let's say that we don't even have outputs, or that this is somehow 0. So then this would be this whole thing would simplify to this delta is equal to WH times this delta. Yeah? And with the only difference that we change the index from t to t plus 1. But then I can say, okay, but then if this is so, then this here is WH times delta H t plus 2, and so on, right? So I would get that under this simplification, I get that delta HT is WH times delta HT plus 1. This is 1s and this is 0, okay, in this simplification. So I have this. But then I can recursively apply this formula again. So I have WH times delta HT plus 2. And then I replace this in the same way, and so on. So I multiply this weight matrix, WH, how often? Well, as often as I, like for the length of my sequence, which is tau, right? Okay, so, well, depending where I am currently. So if I'm at time step, so if I'm at time step 0, then I do it all the tau times. If I am already like deeper in the sequence, well, then much less so. But in general, I have here up to tau multiplications of this weight matrix with itself. So if I do the backpropagation through the from your side, so I do the forward pass through the recurrent block. This is this unfolding idea. Okay, so I unfold for tau steps, and then later in the backpropagation, I propagate these deltas back. Yeah, and what this formula says, okay, if you start at the end, so somehow you get the delta from the backpropagation, you receive the delta that arrives at the end of your cell, and then the delta at the beginning of your recurrent cell will be what you had in the end. So what you have in the beginning for, let's say, delta 0 is what you had in the end multiplied with the weight matrix multiplied with itself tau times. Yeah. Okay. Why is this a problem? So let's see. There is in linear algebra, there is a concept of eigenvalue decomposition. So you can, and every matrix with a certain property, and this property holds for our weight matrices, you can represent as some matrix U multiplied with a diagonal matrix and then times U inverse. This is kind of this is a projection. I project but they exist like a matrix. They exist a matrix U and this matrix here for which I have this relationship. Okay, and these here are precisely the eigenvalues of this matrix. Okay, now what happens is we now say we have this weight matrix. What happens if I multiply this weight matrix k times with itself? What happens is that this this multiplication, I can write it in this form here, and it will turn out that I don't need the k neither here nor here, but the k will only appear on the diagonal. That means that if I multiply this matrix k times with itself, I get something like this. Okay. Now suppose that all of these values here are smaller than 1. Let's say between 0 and 1. What happens if you multiply a number that is between 0 and 1 with itself? It's smaller. Every time it shrinks and it converges to 0. So what we say is that, for your backpropagation, you need the gradient, the net gradient, and the net gradient is this time the net gradient at the beginning of your recurrent cell is the net gradient from the end of your cell multiplied with this matrix here. But this matrix, if the k is large, will have an almost 0 matrix in the middle. So if I might multiply something with an almost 0 matrix, I will almost have a 0 matrix here. And that means that this net gradient then at the beginning of my recurrent block is almost 0. Which means that I don't have flowing gradients anymore and I don't learn anything anymore. This is the vanishing gradient. Yeah, so if
But it will depend on the k, and the k is the levels of the layer, maybe.
the k is
No, the tau, it's the number of layers that you have in the.
not the layers, the number of the sequence length.
Okay, so yeah, okay.
So if you have, so if we want to train on long sequences, then the gradients vanish. So maybe they are strong still in the end of, so what arrives from the end at your recurrent layer is still strong, but as you propagate these in your recurrent cell, these disappear. And then anything that comes before your recurrent cell basically doesn't get any multiplications with anything positive anymore, but only with zeros. So then you can observe that basically you're not able to learn anything for long sequences. So if even the maximum entry in this, if the dominant eigenvalue, if this is smaller than 1, then I have this problem, because I mean, if it's even like this for the biggest one, then it's certainly like this for all the others. And then all the values converge to 0. No matter which matrix norm you have, it can be the Frobenius norm or whichever matrix norm. Okay, so as I have long sequences, then I will not have no gradients anymore. At least if this happens, maybe it doesn't happen, but guess what? It could even be worse, because it could also be the case that the biggest of these values is even bigger than 1. So what if there is an eigenvalue that is bigger than 1? Then, I mean, let's go back to the matrix. So what happens if one of these entries is bigger than 1? Then you have exactly the opposite. Then this blows up. So if it's 2, for example, then you have a sequence of lengths 20, then have 2 to the 20. and that is already, well, 2 to the 20 is still manageable, but if it's 4 or 10, then I mean 10 to the 20 is not manageable anymore. Okay, so then this will hit an upper bound in the machine, in the numerics of the machine. Okay? So in this case, you get something like infinity, yeah, or an overflow. So you get this, which is also what we discussed in the machine learning course, like in the deep learning course. You get this numerical instability, yeah, and this will break the whole. This is even worse because this creates non-values in your backpropagation flow, and then everything is dead immediately. As soon as you have non-values, everything is dead. Yeah. So what we should have is that these lambdas ideally are somehow close to 1. They shouldn't be smaller, much smaller. They shouldn't be much bigger, but they should somehow be close to 1, so that gradients neither vanish nor do they explode. Now, let's see. Yeah. We will not go into the exact math of this, okay? But I explain a bit to you what the problem here is from another viewpoint and why the gated units and LSTMs solve the problem. Yeah. Okay. So one important derivative that is maybe never computed explicitly, like, okay, yeah, it's computed at one point, but maybe not exactly with this operation. But what is important is what is the effect of the current value of the hidden state to the next one. So an effect is partial derivative. Okay, so how does my current internal state influence the next internal state, so to say? Okay, and one can show that this is simply dt times wh, where this here is the, okay, so this is not very well formatted, I have to change it, but this is my weight matrix, okay? So this is my weight matrix, and this here is a diagonal matrix. Has only values on the diagonal that depends on the t, okay? Now, if I see this, then this is the same argument, because I will have in my backpropagation path, I have to multiply this derivative several times, one for like tau times. And that means that in the end, or like in the beginning, better said, I have again this h to the tau. Okay, so this again the explanation why this problem in the standard recurrent unit. So I will, no matter what this is something diagonal. It can have any values, but the point is, no matter what it is, it will be multiplied with something that is close to 0. Okay, and then this whole thing, this whole gradient converges to 0. And this is precisely the step that now improves in the GRU unit and in the LSTM unit. Yeah. So what you have in the gated unit is that the same derivative. So how does my current state or my last internal state influence the next one? This derivative can now be written as this here. It's a bit complicated, and it's not so important to understand every symbol here exactly, but what we have is, what is important is this AT. So AT is a diagonal matrix that only has values on the diagonal, everything else is 0, and these values are these gate activations, okay, between 0 and 1. So here you have a matrix that has only values on the diagonal between 0 and 1. Yeah, and here you have the inverse. And this is multiplied with something, and here you add something. Now the point is, so these are Jacobian matrices. So these are matrices of partial derivatives, yeah, of the of my update vector given the current state. Okay, so the point is I have summation symbols here. And not only multiplication, I have summation. And summation means that something doesn't go away. Yeah? If I always multiply, and the thing with which I multiply gets smaller every time, then I have this problem that things disappear. Yeah? This is where the gradients vanish. But here I don't have I also have multiplications, but I have summations. So now imagine that we can somehow make sure that this thing here will never be close to 0. And then we have 1. Yeah. Because then the gradient does not disappear, no matter how often we apply this. And when would this happen? This would happen, for example, if these are the gate activations here, then this would happen, for example, if we never, if we do not start to remember everything, because remembering everything means that all the gates are close to 0. We do not. Sorry, we start to forget everything. So what we do not want is the recurrent situation, that we only incorporate this one. Okay, so if we when would that happen? If these gates are all closed like 0, then we would not remember anything and we would only incorporate the new knowledge. This is what the recurrent unit does, and we don't want this. So we want these gates to be somehow open, maybe half open. Yeah. Let's say 0.5 for all entries. If we would have 0.5, then we would remember 50%, and 50% would come from the new input. And then we would have, in this situation, we would have a diagonal with 0.5 here in this matrix. Yeah? And if this happens, then this derivative here never becomes close to 0. Yeah. But if these are close to 0, then this can in fact happen, because then my luck depends also on the rest here. Okay. So this is an argument why at least these gated units have the potential to overcome the vanishing gradient problem. Yeah. But the only problem is that we cannot guarantee that he will not memorize. So we cannot guarantee that this thing here will be not 0 at some point of time. And this is where the LSTMs then bring an advantage. So again, I'm not going to say that let's understand the full formula here, but maybe I will, after the class, I will prepare some, let's say, supplementary material. So for those who really want to understand this in depth, which is a very good exercise, then they can do it, but I don't want to cover it here. But here the point is that here I have a matrix, this one, for which we can mainly guarantee that it will never go to 0. So no matter what happens here, no matter what happens here, there are some parts in this partial derivative that will never go close to 0. And that means that no matter how long my sequence is, I will not have vanishing gradients in an LSTM. So, and this is a very strong property. So the LSTMs actually have 2 advantages. It's not like I get 1 advantage at the price of something, but I get 2 advantages. I get a better structure because I can separate the responsibilities of communication to the outside, which is my age, and I have a brain cell. So this in itself is already an important plus, but also I have better numerical stability for training these networks, thanks to this property. So it's 2 fat pluses. What's the downside? It's slow, because I have to, I have so many computations I have to do in every step. So it's much slower than a standard recurrent unit, yeah, by a factor of 10 or so, or even more, maybe 20. And it's not very parallelizable at that point. And the other price to pay is, also not only is every iteration slower, but also I will need more iterations because I have 4 times more parameters to learn than in the case of a standard recurrent network. So, so there is then a trade-off. And one very important takeaway for me is that let's not start thinking like, oh, let's formulate it positively. Every technology we see here has its merit. We do not see any technology only for historical reasons. There are situations where a fully connected network is the best choice. There are situations where a recurrent unit is the best choice. There is a situation where a GRU is the best choice. There is a situation where an LSTM is the best choice. And there are situations where attention mechanism is the best choice. But not only because attention has generated the LLMs, should we say we should always use attention now? And I have, in many problems, achieved much better results with an LSTM than with attention mechanism. Yeah? And if you do not have, and attention is also super slow. It's even slower than this. Attention is good if you, the big advantage of attention is that it can be parallelized. So in attention, I don't need to go sequentially through my sequence, but I can do everything simultaneously. And this is great for parallelization. Here I have to process my sequence sequentially. And this is like a kind of bottleneck. So if I have huge amounts of resources, then transformers are great because then I can parallelize enormously. But if I don't have this hardware, then this advantage is not there.
2 questions.
Yeah.
The first one, I haven't understood why this formula does not depend on the city size. I mean, why there's not a town here in comparison to the last today.
No. There is also a tau. The point is that so here you see that in the recurrent formula, there's also no tau here. So the tau was in this. So we have two views. We have this view, and here you have the tau.
Yeah. The problem was the amount of population with the weight matrix.
Yeah. So, but what happens implicitly is that you multiply these gradients with each other for every time step. So you basically have this result for every time step and do a multiplication. Only that I don't show it here on the slide. You also have it. Yeah. So here you also have the tau. I don't show it because maybe I can extend this somehow. But here you have to do. So you have this for every. Here I anyway have to update this because here actually this should be the same letter. So h and h minus 1, or this should be a t, ht and t minus 1. Now you have to actually you will multiply this for every step in your sequence. So you do it for you need this for t equals 1, for t equals 2, t equals 3. You compute these and multiply all of these. So you do it also here, and also in the other. But the difference is that in the other one, the values are so stable that even the product will not converge to 0. Why is this the case? Because if you have, look at this, if you multiply this now, let's do it with a very simple example. So let's just say, let's do 3 different colors, one for the recurrent case. So let's say that your formula is, which symbol, maybe we use alpha. So let's say that alpha t is a t, okay? Now, if, and maybe this is even somehow, this is bound. So then if you say that I have alpha t times alpha t minus 1, then this is basically, let's make this independent of the t in this case. Even then this would be just a times a, so that would be a squared, okay? And now, if you do this several times, then things go bad. Now suppose that your alpha t is a plus b. Yeah? Then if you multiply alpha t times alpha t minus 1, then what happens is you get a plus b times a plus b. Yeah? And this is a squared times 2ab plus b squared. Now, if one of these guys here is stable, so if you can make sure that this is not close to 0, no matter how often you do this, you can make sure that one term will not disappear ever. Yeah, but this is because of the sum here. Because here you don't have, so here you don't have this vanishing effect. But I think I will make a kind of additional clear where this point gets clearer for this concrete example.
But I got it, because A and B will be bounded to between 0 and 1. It doesn't matter if A or B are close to 0 there. It not vanish because it remains the term 2 plus A plus B. So it's fully
Yeah. Okay, so by the way, all of this was in the 90s. So we're not talking about recent research here. This was, I think, 95 or so, or 97. But yeah, of course, at those times, it was super difficult to do these computations with the machines at the time. I mean, you can imagine like 100 megahertz and 32 megabytes of memory. So a bit difficult. And we didn't have the data. Okay, but this technology is not recent. Attention is, but this one not. But it's still very competitive and very useful for many problems. Okay, and so the homework exercise will be also to compare them. So not in grade scope, because in grade scope I cannot grade that, but let's say in the oral exam, I will ask you, okay, so what did you observe when you have, if you compare on the sequence sorting problem, for example, a dense network, an RNN, a group, and an LSTM. So what you should do is create 4 learning curves. Yeah, 1 learning curve for the fully connected, 1 for the RNN, 1 for the group, 1 for the LSTM. See how is the difference? Maybe one starts much higher, but converges to something better. Maybe it takes a long time, some converge faster, so on and so forth in terms of runtime. So this is a good lesson to learn in your homework exercise, to compare these just on simple problems. Cool. Okay, that was entonces, éxito, chicos. Gracias.
Gracias. Chao.
Yes. Bueno, the question. Is there any kind of framework or rule of thumb to choose a particular method, a particular architecture, a particular problem?
I'm working on that. So I've one co-supervised PhD student in Germany, and he's working on time series, and he said, why is there no automatic machine learning for picking a good architecture? So we start with him working exactly on that. So that say, I don't decide whether I want to fully connected or recurrent network, but he will try different architecture automatically and try to figure out which is the best one for my problem with the given data at hand. Because for LSTM, I also need more data than for a recurrent network, because I must train more characters. Muy bien. Excelente. Descansar. Sí, sí. Sí. That's not good. This is what I